Next, we have Professor Michael Wolf, Professor of Econometrics and Applied Statistics at the University of Zurich. Professor Wolf specializes in statistical modeling and data-driven approaches for macroeconomics analysis. His research interests include resampling-based inference, multiple testing methods, the estimation of large-dimensional covariance matrices, and financial econometrics. His work has been published in leading journals such as the Annals of Statistics, Biometrica, and Econometrica. Please welcome Professor Wolf.
Thank you. How do I get my talk? Next. Oh. No. This is it? Okay. 25. If you have the time, do you give me the time?
I will tell you when it's 5 minutes left.
All right, good. All right. Well, honored to be here as part of the Symposium. It's really a great venue to meet people from all kinds of different walks of life, not only academics, which is what I'm used to when giving talks and academic conferences, but this is different. It's really great. And I'm also honored to represent ADIA Lab. So thank you for having me. And it's about forecasting. So this is a very specific talk. It's not like an overview talk like we had many, and I'm not a policy maker, and I don't have, a great wisdom for the planet in general, but it's a very specific talk, how to forecast inflation and how to do it better, and how to take machine learning and improve it for a very specific task. All right, so here's the outline. I think the motivation, I don't really have to motivate it too much. People understand that forecasting inflation is essential for many walks in life: economic policy, financial markets, broader societal stability, and also to make money. So there are industry players, hedge funds, that make money based on forecasting inflation. So if you can do it better, it'll be good for many different applications, right? What have people been doing for a long time, historically for many decades? They have used univariate methods, meaning you can use the value of inflation today and inflation in the past to forecast what is coming, right? So there are many examples: the random walk, autoregressive model. The other one, you can read it, I probably can't pronounce it correctly. And until recently, these univariate methods dominated. But then with machine learning methods, people have shown that you can do better, finally, after a long time. So you take a large number of inputs, other macroeconomic variables, many of them like 100, and then you may take lags, so total number maybe 400 or 500s. Then finally, you're able to outperform those traditional univariate methods. In particular, the one that is the leading one among the machine learning methods, the random forest. We'll talk about it briefly, what it is. And then the goal of this talk is to tweak it, to enhance it, to make it even a little bit better with very simple tools. Simple, yet effective. All right, what is the random forest? Well, the forest is something that consists of many trees. So it starts with many individual forecasts, which are then simply averaged to get one number, right? And the individual forecasts are made by so-called regression trees, and we'll say what that is. And then how do you get the many? We'll talk about that. There's a certain random mechanism to get you many trees. So trees, forest, many, and random, hence random forest, right? What is a tree? A tree is trying to predict something based on input. So we have a very simple example. What we're trying to predict here is the log salary of a baseball player, and we have two inputs: experience, the number of years the player has been in the league, and the number of hits in the previous season, right? And then what we see on the left is a so-called regression tree that does successive splits always according to one of the inputs. Right here, the first split is according to experience, and the tree says less than 4.5 years, we go to the left. More than 4.5 years, we go to the right. And here we make a second split according to hits. Less than 117.5, we go to the left. More, we go to the right. So in the end, we're partitioning the sample space of the inputs, which is here two-dimensional, into three regions. That is region 1, and then that is region 2, and that is region 3, right? And a typical tree would keep on splitting more and more times. So that is just the principle. And where these numbers come from, why 4.5? Well, there's an internal algorithm that picks the best number at this particular point. And there's an algorithm that picks the best number at this particular point, right? So we have partitioned, according to these splits, the sample space into three regions. Then a new player will come in. Well, we drop the new player down the tree, right? We know every time to go left, go right. And then the new player will end up in one of the three regions. And then we take the average value in that region to predict, which is 5.11 here, 6 here, and 6.75 there, 7.4, right? So that is one individual tree. And the advantage, these trees are flexible. They can model nonlinear relationships, right? Classical standard linear model might be misspecified, but trees are really flexible. They have low bias, meaning they don't aim too high systematically. They don't aim too low systematically. They're sort of right on average, but they have high variance. You know, they can be quite noisy in their predictions. Then the statistician, when a statistician sees low bias, high variance, the statistician wants to average. Give me many trees, and then I average, and then I reduce the variance, right? I become more accurate. But how can we get many trees? We only have one data set. If I build a second tree in the same data set, I get back the same tree. Not helpful, right? And the solution is this, that we create artificial data sets by resampling from the observed data at random. So that one player may appear 2 times, another player not at all, one player 1 time, right? We replace at random with replacement, like taking urns, taking balls out of an urn with replacement. That gives us a new data set, and then we can grow a tree on these artificial data sets. And then further at each split, we don't look at all the possible inputs. We just take a random number and then a random subset. So there are 2 random schemes, and then we average, and that's the random forest, right? So the random forest takes the simple average. You have, say, 1,000 trees, say 100. Everybody gets weight 1 over 100. The simple averaging. The scheme is simple, it's robust, it works well, it's not optimal, right? So we're trying to find a better weighting scheme. And there's a nice analogy, portfolio selection, right? People at ADIA investing in a universe of assets, such as stocks. You may have a large number of stocks. Well, there's this old, the standby oldie, and some people still claim goldie. The equal weighted portfolio just invests the same amount into each stock. Well, it's simple, it's robust, it works well, but it's not optimal, right? A portfolio manager wants to find a better weighting scheme, and they do exist, or people wouldn't be in business if you couldn't perform the equal weighted scheme, right? And now here, I think I'm going to make a nice sort of marketing pitch, because what have people done over the last decade or two? They have shown how to use machine learning methods to improve portfolio selection, right? Last 10, 15 years, books have been written, one by Marcos, one of the first ones. You can use ML to improve portfolio selection. Here today, we will return the favor. We're going to use portfolio selection to improve a machine learning method, namely the random forest, right? How? And then where does the name come from? In general, so now it has to be a little bit of math here and there. I can't completely hide it, right? So I'm putting math alert. We want to forecast a variable, inflation based on many inputs. So there are D inputs, there can be many, so it's a vector, right? And then we have individual trees, little p of them, think 100, 500, you know, not a million, like 100 or 500. And then the random forest uses equal weighting, right? 1 over p for each tree, so EW equal weighting. And all we want to do, use different weights, Wj, right? So we have a vector W of individual weights. They do sum to 1, but they don't have to be equal. And in particular, we do allow for weights to be negative. So sometimes people get scared in that literature, oh, negative weights for a forecast, what are you doing? But if it helps the accuracy, and mathematically it's not illegal to use negative weights, right? Okay. So a bit more math. Every tree will make a mistake, right? That is the true number that will come. This is the forecast, and there we have the mistake that tree J makes. We put the mistakes into one vector, and the vector has a mean, the expectation, and a variance covariance matrix. So that is also a vector, but that is a matrix. And then according to a certain criterion, the mean squared error, which I'm going to skip the details, what is the best weighting scheme? The best weighting scheme is the solution, to the simple problem. Do you want to minimize W prime U squared, which is a squared bias, W prime sigma W, which is the variance, under the constraint that the weights must sum to 1. This problem can be solved very simply, very quickly, and then you get the best collection of weights. The problem is, in practice, you don't know mu, you don't know sigma, right? It's a bit like portfolio selection. Very simple, the suggestion somehow from past data, you need a set of training data, otherwise you have no chance, right? So you need a set of training data, and from the training data, you get estimators, mu hat, you get estimator sigma hat, and stick it into the same formulation, but you add one more constraint, right? The constraint is that the sum of the absolute weights may not be bigger than some constant. Constant, something like 2 for us, right? And that comes from finance, from the financial portfolio selection literature. They call it a gross exposure constraint, you know, like how leveraged your portfolio is allowed to be. In the extreme case, if kappa is 1, all the weights must be non-negative, right? In the other extreme, if kappa is infinity, the weights can be whatever they want. And some could be very big, and some could be very small, right? And that could give bad performance out of sample. So we want to hedge against extreme weights, right? Because we have noise in mu hat and noise in sigma hat. We don't have the true inputs, right? We have estimated inputs, and hence we want to hedge. And in practice, we like round numbers, simple numbers. Take 2, and that's it, right? So estimate mu, estimate sigma, stick it into this problem. You can solve it in no time. And so you have the weights for the individual trees that are no longer equal, and some will be negative. How does it work in practice? So we want to forecast inflation, right? Very influential paper 4 years ago. They have shown that machine learning finally can outperform these univariate methods, number 1. And number 2, among these many machine learning methods, and some are more complicated, like neural nets, but the relatively simple random forest is the leading one, right? But then we talked to these authors, have you tried, non-equal weights? Can you do even better? They said, yeah, we tried, but we couldn't do it. Right. So we had a challenge. Can we do it? We're basically following their empirical study, so we have monthly data going back to 1960. At every point in time, as I said, we always need training data. So at a given point in time, we use the last 30 years for training individual trees, and then getting the standard random forest and getting the hedged random forest. And then we forecast what is coming. And the variables are so-called features, which are basically 100-something macroeconomic variables like inflation, unemployment, gold price, many others, and then we lag them 4 or 5 lags, so that we get a total of roughly 450. And then we start in 1990, we train and we forecast, we compare, and then we roll month by month. We shift 1 month, use the last 30 years, we train, we forecast, we compare. Inflation is defined like this. It's basically it's just like a financial return, right? We have a price index. We take the percentage change from 1 year compared to this, we have monthly data. So it's the change compared to 1 year ago, and then -1. So it's a return. If you will, it's a financial return on a price index, right? That is what central banks and policymakers do. And we have 6 of them, 4 from the US and 2, because we work in Switzerland. We took 2 from Switzerland. And if you like very long and ugly acronyms in inflation literature, you would be very happy, because I'm not even going to try and pronounce what it is. But the 2 from the US, so this is all items, everything, and then without food and energy, headline and core, right? This one, everything, CPI, without food and energy, headline and core. And then we have the one from Switzerland. I mean, look at that, goodness me. Everything without food and energy. So that's what people do in inflation. There's everything always, and then without food and energy, which is less noisy. So you see here, the headline measures are in solid, the core measures without food and energy dashed. So you see the dashed ones, they don't wiggle as much, because food and energy are very noisy. If you leave them out, inflation is a bit more stable. Okay. Similar patterns, right? In like pink, these are periods of recession as defined by official policymakers. Right, now maybe for the last time a math alert, we want to estimate mu and sigma from training data. We have time series data, obviously data is collected over time. We have to take it into account. So just for those from the literature who want to see a little bit of details, we start with so-called exponentially weighted moving average estimation, which means we give more weights to the recent past, like the last month and the month before, than the year ago, or let alone 10 or 30 years ago. So we don't give equal weights to the training data. And there's a certain parameter that determines how fast the weights decline, and we use 0.15. We have monthly data. For daily data, it should be a smaller number. Again, portfolio optimization, portfolio selection. So risk metrics, these people had come up with this estimator in the context of finance, how to estimate financial covariance matrices, right? So again, we're borrowing tools from the finance portfolio selection field to bring it to machine learning, right? And then we come further, we post-process by linear shrinkage to make the estimator for mu and sigma a bit more stable. Where's Olivier? Raise your hand. So with him, I've been working on shrinkage. I've been told shrinkage is not a good name. It's not our name, 5 minutes. We didn't invent it. But it's not a nice name, but it works really well. So that's a detail to make the estimators a little bit better. How does it work, right? We're going to forecast horizons from 1 to 12 months ahead. That's what policymakers are interested in. Up to 12 months, you can forecast with statistical models. Beyond that, it becomes too noisy. I'm going to skip that. There are 2 approaches. One works better, but that's not important for us. We need a performance measure, right? Every time we're going to compare, pi is the inflation, right? The forecast, pi hat, minus the true number, that would be an error term, right? And then we're going to sum the absolute errors over the entire out-of-sample period, and then we average. That is called the mean absolute error. Obviously, you would like a small number, right? The number by itself is hard to interpret. But what is interpretable is the ratio. If we take upstairs, the mean average error for our new method, the hedged, and downstairs the old-fashioned method, the standard random forest. If we are below 1, we are better. And we can tell by how much, right? It's sort of a percentage reduction in mean absolute error compared to the old method. We want to see numbers below 1. When we did it, well, we have in total, we have many, many, many numbers because we have 6 inflation measures and 12 horizons, 1 month ahead, 2 months ahead, right? 6 times 12, a big number. So we expected some ratios above 1, hopefully a few, and hopefully many below 1. But what we get, all of them are below 1. Even those, right, I can't display all the H's, only 5 out of 12. They're all below 1, right? So we always outperform. There's nothing to lose. And on average, over the 12 months, well, it works better for the core measures. We almost get 10% reduction. Here, 5, 5, 6, 4, 9. So in that context, because we're starting with a method that's very good already, and with a relatively simple tweak, we can get these kind of reductions. So I think that that's a good achievement. And there are these practitioner journals for national banks, and our article has been featured there, and people seem actually quite excited that we can do quite a bit better without having to completely reinvent the wheel, right? A simple tweak. And we can also, this is over the entire period. Now you could say, well, you outperform over the entire period from 1990 to now, but maybe you underperformed when it was really of interest. Maybe you underperformed during times of crisis, right? And that wouldn't be nice. So we're looking at the performance over time. So from the starting point, 1990, to any given point in time, we look at that sum of differences, right? So that means until that point, what is the out or under performance, right? We can plot this over time. So we'd like to see these lines just going down, 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 but maybe sometimes they go up. And so we see they do go down. I mean, in the end, we always end up below 0, that we know from the table. But we also see the behavior, so typically they just keep on going down, though there may be points, some periods where they go up a little bit. You don't always win at every single point in time. But look, especially during the financial crisis and after is when we get the biggest drops, right? So when you probably really care the most, you outperform the most. And hence, I'm trying to, coming from Switzerland, I must stay within the time limit. So we do know the last 10, 15 years, machine learning can really improve portfolio selection. But now today we have returned the favor, maybe for the first time, I don't know. So we have shown that portfolio selection can improve machine learning. You combine the two, you get the hedged random forest, and we have seen it does outperform consistently, right? Consistently and safely the standard random forest for this task of forecasting inflation. And I just want to leave you with this. It's a very influential paper that really has shown for the first time that with machine learning you can do better than these classical methods. So we owe a lot of thanks to these people. And then, thank you.
Thank you so much, Professor Wolf, for the great presentation.